Part two. So our speaker is Dr. Christina Knudson. She's an assistant professor at the University of St. Thomas, an alumna of the University of Minnesota School of Statistics, and a co-organizer of the Twin Cities chapter of Our Ladies. She researches likelihood-based inference for generalized linear mixed models and termination rules for Markov chain Monte Carlo. She's the creator and author of R packages, GLMM, and stable.gr. In her free time, Dr. Knudson enjoys doing yoga, running, biking with me, rock climbing, walking her Siberian Husky, drinking coffee, eating avocados, and being a stereotypical millennial. Please welcome Dr. Knudson.
Thank you, Lindsay. I'm super excited you're all here. This is the first year of this conference, and Lindsay's done an amazing job organizing it, so you should definitely thank her later and talk to her at some point. So if you weren't here for the first session that Anting went through, that is totally okay. Just a super quick review of some of the things from part one. Some nuts and bolts pieces. First, we have the prior distribution. So that represents any information that you know before actually collecting data. So this can be expert information, or if you don't know anything, that's okay. You don't have to have any prior information either. Then the data that you collect is represented in the likelihood function. And then you combine the likelihood and the prior to get the posterior distribution, which is a distribution of the parameters given the data. Then we use this posterior mostly as our as a thing that we use for inference. So we could look at the posterior mean, the posterior median, variance, whatever. And then Anting talked a little bit about conjugate priors. So those are convenient because you can combine them with the likelihood to create a posterior distribution that's pretty easy to work with. So for example, if you have a normal prior and a normal likelihood, then you can end up with a normal posterior. So if you have like a pretty basic example, then that's great to use a conjugate prior. Most of the time, once you get into the more complicated real life situations, then it's a little bit hard to use that conjugate prior. Okay, so what are the basic Bayesian steps, assuming that you don't have a conjugate prior that you can work with? So first step, you select your model, and that requires also specifying your prior distributions. Then you can approximate the posterior using Markov chain Monte Carlo. So if you have a conjugate prior, you don't have to do this approximation business. You can just go ahead and use that posterior distribution straight up. But if you don't have a conjugate prior, then your posterior is going to be kind of very tricky to work with, analytically intractable. So you'll probably want to use MCMC to approximate your posterior distribution. Once you do your approximation, it's a good idea to kind of use your brain and think about, okay, is this approximation good enough? Like, have I run this long enough? Do I need to do any other things with it? And we won't get too much into that. And then finally, once you've decided you have a good enough posterior approximation, you can use that approximation to conduct your inference. And like Anting said, you can code all this yourself, or you can use one of the many R packages that's on CRAN and elsewhere in the universe. Okay, so Anting went through this a little bit already. So approximate the posterior by using MCMC. And that general process looks like you need to choose some starting value. Once you choose a starting value, you let this thing run. It will select a new value, decide whether or not to move to that value. So the exact mechanics of this just depend on the kind of MCMC sampler you're using, but it will calculate a probability to decide whether it should move to the new value, then generate a random number, and based on that, decide whether to move to that new value or not. So at each step, it can either move or stay in the same place. So we have some packages that will do this MCMC sampling in the context of your model, so it makes it very easy. So for example, the MCMC pack will do specific methods of Bayesian inference. So for example, if you want to do a linear regression or a logistic regression or other like more specific types, then MCMC pack is very useful for you. If you are getting into like a very complicated Beasley model, there's not going to be necessarily a nicely packaged set of functions for you to use. And so you'll have to find your posterior distribution and sample from it yourself. And one tool that you can use if you don't want to write up your own sampler, you can use the MCMC package, which has like the metrop function and other functions to do your sampling for you. So you provide the log, a normalized posterior, and it will do the sampling for you. Okay, so right now I'm going to talk more about the MCMC pack, just because it's a little bit more accessible and requires a little bit less like math and extra thinking. Okay, so yeah, nobody likes thinking. So to fit the Bayesian linear model with MCMC pack, there's the function MCMC regress, and the mechanics of it, the syntax of it looks pretty similar to the LM function. So if you've been using that, then it's very easy to slide right into MCMC regress. So you have response tilde predictor. So if we're doing our bikes example, we have number of registered riders and the perceived temperature, or the temp underscore feel, and we're using the bike data. So in case you weren't here in the first session, this bike data is bike share data from DC in 2011 and 2012. And so they have the daily number of riders, and then things like what was the temperature that day, what was the perceived, like there's the thermometer temperature, and then once you take humidity and stuff into account, like what's that like feel like, so that's temp feel. And then a whole bunch of other variables as well. So if we want to make a linear model just with the perceived temperature, then we can do that, and I just called that bike mod. And just so that you can see what like multiple linear regression looks like, I made a second model down there and incorporated humidity into that. So if you want to keep it super simple, this is the bare minimum of what you've got to put into MCMC regress. So as you can see, if you're familiar with LM and don't know much about Bayesian statistics, this is super easy. And that's a good thing and it's a bad thing, right? If you're not thinking at all, that is extremely dangerous. So that's definitely something to think about. Okay, so it's a good idea to talk about like what are the defaults that are being hidden when you just run that basic MCMC regress with just the two arguments there. So first thing to know, what is the Monte Carlo sample size? It is 10,000, and that's the Monte Carlo sample size that's going to be retained after burn-in. Then the next default is a burn-in of 1,000. So that means that it'll sample 1,000, throw away those first samples, and then continue sampling from that point. So 1,000, throw it away, get 10,000 more. Then the next argument is thinning. So thinning is when you discard some samples. So like if you were going to discard like every 10 samples or only retain one out of every 10 samples, then you would be thinning your sample. In a lot of cases, that's not, like thinning is often not a good idea, but in some cases it actually is a good idea, surprisingly. Art Owen gave a really interesting talk last year at the conference in honor of Charlie Geyer, who's a professor here at the U of M. So actually sometimes thinning can be a good idea, but I would definitely think about that rather than just like thinning straight off the bat. Okay, next, beta.start. So the default for that is NA, and what that means is that it'll go out, use LM to calculate the OLS estimates and use those as the starting values. That's the default. And then for the prior, that's these final two bullet points here, the prior mean, it assumes is 0, and then it use a prior precision of 0, and precision is just 1 divided by variance. So if we have infinite variance, then that's a precision of 0. And what this is saying is like, we're just gonna have a totally uninformative prior. We're not gonna insert any expert or whatever information into our prior distribution. Okay, so that is what's going on behind the scenes. There's more too, but I think these are like the most important ones. Okay, questions so far, just in case. Yes?
So does it take a long time to run? Or
No, this one takes pretty, like, I don't know, 2 seconds, something like that. Yeah, it's pretty fast.
Okay.
But you're right, sometimes MCMC can take a really long time because the sampling for more tricky things, for bigger models, takes longer, yes. Any other questions? All right. So if we use plot, so I called this, remember, bike mod. If we plot bike mod, it'll give us 2 columns here. The first column is a trace plot. So that shows us the different values that our parameters take on. So the first row here is the intercept, and then the second row is the slope. Third row is for the variance. So we can see the different values that we've traveled through in our MCMC, and then we have the histogram over in the second column. So we have our approximated densities there. So this is useful. It's always a good idea to plot your data. Hopefully you've like kind of figured that out. So it's always a good idea to look at what you're working with to see like, okay, did something disastrous happen? And lots of times in a plot, you won't always see the disaster, but if there is a disaster, or if you do see something, you know there is a disaster, if that makes sense.
What does it look like when a disaster happens? In a trace plot.
Well, like say you got your density and it was really like choppy, granulated, then it would be like, okay, I should definitely sample for more than like 1,000 steps or something like that. And especially when you have, so this is like a pretty baby example because it's just linear model with a single predictor. But once you have a lot of parameters in there, then it can be really hard to update and move in your MCMC sampler. And so if it gets stuck somewhere for a long time, then you might not end up with actually that much like variability in your density. Good question. Okay, so we used MCMC pack then to make our linear model, and now we can use some other packages. So I'm going to give you like a tour of a few different packages. So once you have your MCMC sample, you can assess that approximation. So we kind of did that visually just a second ago, but there's like, you know, more quantitative things to do. So for example, there's this package, stable GR. So if you've done like Bayesian stuff, you might have heard of the Gelman-Rubin diagnostic. So that assesses convergence. In particular, like it tells you like, do we have enough samples to give a good approximation of the posterior distribution? So here I'll just first show you like how to use that, and then we'll talk about the different pieces of it. So we just say stable.gr, put in our model, and we get something called the PSRF, the NPSRF, and then it also gives us the posterior means and the effective sample size. So first let's talk about the PSRF. So a big question when you're doing MCMC is, did the sampler run long enough? And there's a whole bunch of different diagnostics out there to try to address this question of, did we run it long enough that we have a decent approximation? But the one we're going to talk about here is the one that's most frequently used and cited, Gelman-Rubin, and it was first made in 1992. And what it essentially boils down to is the square root of chain length minus 1 divided by chain length, plus the between chain variance divided by the within chain variance. So you can see that this first piece, chain length minus 1 over chain length, that's going to, once you have a decent sample size, that's going to be approximately 1. And then for our second fraction there, between chain variance divided by within chain variance, once we run our chains long enough, then the different chains will look pretty similar. And so we shouldn't have that much between chain variance. So as you run this MCMC sampler long enough, the between chain variance decreases, meaning that this second fraction here is going to go down to 0, and this is going to go to 1. So once you run it forever, this PSRF will go to 1. Okay, so how do we calculate that PSRF? So stable.gr bike mod, and then if we just want to isolate PSRF, use the deadly $sign, and we get 1 for each one of these parameters. So this is the PSRF for the intercept, the second one is for the slope, and then for the variance. And so these are pretty small, and we'll talk more about like what is small enough in a second. And then also one cool note, even though the bike mod that we made, we constructed that with a single chain, we can actually calculate between chain variance with a single chain, and that's thanks to methods like batch means variance estimation. So just a side note if you think that's cool, because I do. All right, so In this previous slide, we looked at the PSRF and we said, here's the one for intercept, for slope, for variance. Now we can look at the multivariate PSRF. And so that pretty much takes the information from the 3 or however many components you have, smashes it down into a single number so that you don't have to go looking at all of them when we have a pretty big model. So we get our multivariate PSRF, and it has a similar idea here. It will decrease to 1 as the chain length increases, and so you can decide to stop when you have a small enough MPSRF. So that brings up the question of how small is small enough? So we look at this number 1.000006. Is that small enough? We can decide if it's small enough by using target.psrf, also from StableGR. So we tell it how many components we have. So we have an intercept, a slope, and a variance. So we have 3 components, or p equals 3, and we're running a single chain in this bike mod MCMC regress. So we have m equals 1. So we crunch that out and we get a target PSRF of 1.000062. So once our MPSRF hits that number, we can terminate simulation. Okay, side note, in case you have been playing the Bayesian game for a while, then you might have heard the conventional wisdom that you can stop once your PSRF or MPSRF hits 1.1. That is, now we know better, pretty much. Like, they didn't know how to make a good rule before, so they're like, okay, 1.1 sounds reasonable. Now we know that there are better ways to do it. So if you use the target.psrf, that will give you a much safer rule for termination. Generally, 1.1 was far too early. Okay, so we can decide if we have enough samples by looking at MPSRF and comparing it to target.psrf. I know I myself don't really want to like compare 2 numbers. I'd rather just roll it all up into one fell swoop. And so we can use the n.EFF function also from stable.gr, or also from StableGR, to check whether the sampler ran long enough. First of all, effective sample size. Remember, this is MC, so we have correlated samples, like draw 1 is correlated with draw 2, and so on. So if we want to know how many samples that are uncorrelated that would produce the same precision as our correlated or MCMC sample, that's effective sample size. So we ran this MCMC model for, I can't remember, I think it was like 10,000 steps, and we see our effective sample size is about 9,000. Okay, so that's a fun little thing in case you are interested in effective sample size. In particular now, to see whether the MCMC sampler ran long enough, we look at our second argument here, which is converged. So it says true, so that tells us our sample did hit the target PSRF. So in other words, we've run it long enough, we've hit that threshold, now we have enough samples to pretty accurately approximate our posterior distribution. Okay, say this didn't say true, say that it said false, then a natural question would be, okay, well, how much longer should I run this? If you need to run it longer, then this n.target will tell you how many samples you need to hit your target PSRF. And of course, this is an approximation, so if it says like 6,702 and you do exactly that many and it ends up you needed 6,707, then like that's kind of just how it goes. So just know it's like an approximation based on what you have collected already. Okay, so we have these 2 tools and they're pretty much going hand in hand for deciding whether you have calculated enough samples to accurately approximate your posterior distribution. Okay, so now that we feel pretty good about our posterior approximation, we can get into like looking a little bit more at our sample, so we could get some basic model info. And now I'm going to talk a little bit about the MCMC-SE package, which works in particular for single chain setting. So if we look at the mcsc.mat, it'll give you the estimates for the intercept, slope, variance, whatever other parameters you have, and then your Monte Carlo standard error. So we want to make sure that we have enough samples that our Monte Carlo standard error is pretty low. And so that's what this is looking at. So remember that as the chain length is increasing, then your Monte Carlo standard error is decreasing. All right, another interesting thing to look at is the covariance between the parameters. And it makes sense that like the slope and the intercept are correlated with each other. So we can check out the covariance here by using MCSE.multi. And if we look at the first argument here, or the first item in this list, we've got the covariance matrix. So we've got intercept, slope, variance. And that's also what's used to get some other standard errors later. Okay, and then if we continue to look at like the connection between the different parameters here, we can check out the joint confidence region for a pair of parameters. And this is again in MCMCSE. So we can plot our joint confidence region. And here I'm plotting the joint confidence region between the intercept and the slope. And so we can see that these are definitely pretty, they're not independent of each other. They are related to each other because our oval is pretty angled. Okay, Anting talked about how you can create credible intervals or credible sets. If you want to create those, or just more generally quantiles, then you can do something as easy as just using the quantile function, which I believe is part of stats, which the stats package, which is always just like in your R environment. So you can use quantile. You give it, say I want to look at the slope, then I would give it the second column here. And if I want a 95% credible interval, then I can give it the 0.025 and 0.975. So this would be a 95% credible interval for the slope. Another way to create a credible interval, and the way that we'll create the shortest credible interval, uses the highest posterior density. So if we have a really skewed distribution, then it doesn't make sense to choose like the middle 95%, because maybe you'll get a really long credible interval. So sometimes you'll want to choose the highest posterior density so that you can create the shortest credible interval. So that's in the HD interval package, and use the HDI function and just input your bike mod or whatever model. And the default is 95%, but you can definitely change that. Okay, so in this bike mod one here, we see that the 95% credible intervals are pretty similar, whether you use the middle 95% or the highest posterior density credible intervals. And that's because if you remember a few slides back, I'll just quick show you. Back here, we had a pretty symmetric looking distribution, so it's not surprising that these two methods are yielding pretty similar results. Okay, so we can get quantiles. Something that I learned in grad school that in the real world sometimes people forget is that standard errors are always a good thing. You don't want to just have an estimate with no idea of like the certainty attached to it, right? So it's good to go out and get a standard error. So if you want to calculate the standard errors for quantiles, the Monte Carlo standard errors, you can again go to that MCMCSE package and get the MCSE.q.match, so the Q for quantiles there. So you give it the model that you're using and the method. So I used batch means here. We won't talk too much about that. And then whatever quantile I want. So say I want the 2.5 quantile, 2.5 percentile, then we can go out and get that. And so here's our estimate and then the standard error for that quantile. All right, so to kind of wrap up then, what were our basic Bayesian steps? We go out, we decide what our model is going to be, we select some prior distribution, and we didn't talk a lot about that, but that is a very important step, selecting your prior. You approximate your posterior using MCMC. You decide whether your posterior approximation is sufficient. So do we have enough samples? So you could use that n.f or stable GR. And then you can use your posterior approximation to conduct inference. So we saw like how to get means, how to get quantiles, how to get credible intervals, how to get standard errors for credible intervals. And then some R packages just to kind of touch back on what we checked out. We have MCMC pack, And that, again, was for like, that's what we used to use MCMC regress to get our Bayesian linear model, and also Anting used for the Bayesian logistic regression. So that was the one that I said makes it super easy, but it's a little bit dangerous when it's that easy. Then we have MCMC, which was for that general MCMC sampling. Stable GRs for once you have your sample, you can assess the posterior approximation, get your Gelman-Rubin diagnostic, look at effective sample size. And then the package MCMCSE is for conducting multivariate analyses on the posterior. So like getting quantiles, getting standard errors for those quantiles, stuff like that. All right, and I think we have plenty of time for questions. So bring it on. Thank you. Yeah, Kim.
So these days there have been a lot of packages more on our one you have to show to
totally.
run Bayesian statistics. So the two I'm familiar with are Ajax and Astan. I'm just curious, do these packages also work with the outputs from Ajax and Astan or other Bayesian packages and others?
Great question. So the stable GR, that will take anything that's like also CODA output. So you could give it just like a matrix of your MCMC sample, or if it's CODA output or like that format, then that'll work. Yeah, so I should probably check like what RJAGs and Stan output, but yeah.
JAGs will give you something you can use. I don't know about Stan.
Yeah.
I think you can get the matrices of the MCMC.
Okay, makes sense. Yes.
So with the LM and GLM, you have the predict function to make prediction.
Mm-hmm.
Does the predict function work with MCMC, or how do you get new predictions out of your model?
Good question. Do you know if predict works for this?
Choose the posterior predictive distribution to do prediction or math.
Yeah, so predict pretty much just like does the matrix multiplication for you. So and like the predict, it's not like a single function, so there's like hidden within it, it's like predict.lm, and so if you have like an lm object, then it will use that, or if you have like predict.glm. So I think it depends on like what the class of your like resulting model object is. Yeah. Other questions? Yes.
Can you go back to your 95% interval and kind of explain what is the inference, what are the results? How, like,
Oh yeah, that's a good idea. Yes.
To like traditional linear model.
Totally. So let's just talk about this first one here. So our 95% credible interval or credible set is 51.4 to 64.4. So that's saying that there's a 95% probability that our slope is between 51.4 and 64.4. So someone was saying, I don't think that, or someone was claiming they didn't think that Bayesian was as intuitive as frequentist. And I think when it comes to interpreting credible intervals, it's a lot easier to interpret a credible interval and to understand and digest that credible interval than like a confidence interval. Because for a confidence interval, it's like, okay, if we repeat this process a bajillion times, then about 95% of these intervals are going to contain the true parameter value. Here, it's much less of a mouthful. It's just, okay, there's a 95% chance the slope is between 51.4 and 64.4. And then same interpretation here, just different numbers. Yes. Sure. You. I don't know.
Back to the question about new predictions. Can you pull out the maximum posterior to maximum posterior to do predictions on? Would that be more likely things? Can you do that in here? Or just start. Can you pull out the maximum posterior predictors?
Yes. There's definitely a function. I'd have to hunt it down. I don't know, like, ever remember where things are, but yes.
Okay. I'll stop.
Okay.
It's kind of a weird question, but I try to figure out how to teach things. And if you had success sort of teaching the Bayesian like sort of at the same time as you're introducing students to frequency statistics, or do you kind of keep them separate, or do you have that in a different class, or what do you feel like is effective and good practice?
Great question. So I've been at St. Thomas for 2 years, so not enough time to like shake things up and make them do crazy things. So we definitely take the approach of mostly teach frequentist, and then once they have a couple classes in that, then there's a like a optional class of Bayesian. In one of my like junior-ish level classes, I introduced the idea of Bayesian stuff, but just in the very much like conjugate setting, like, okay, beta, binomial, what's the posterior, and like kind of really basic stuff like that, but like no computation. And I think that's very hard for them to get in their heads, but I think it's mostly because they're a little stuck on the just like algebra of it, of like, oh yeah, that's how we, you know, combine the exponents for a common base or like stuff like that. So it's hard to say like how much of it is like the actual like Bayesian stuff is hard and how much of it is like how much is it hard for their, I don't know how to say this, like, is it the ideas of Bayesian that's hard, or is it like crunching all the numbers out? Yeah. Yeah, Kim.
So I think Anthony already touched on this a little bit, but I also want to, I'm curious if you have anything to add on like the examples of when you would want to use Bayesian versus frequentist or the other way around, just like some real life examples.
Yeah, so this touches on this idea of like, okay, sometimes there's this like big fight between Bayesians and frequentists, like not anymore so much people getting into fist fights, but like apparently back in the olden days, like people would actually like punch each other over it. So it was like quite a contentious topic. And the way I see it, like I don't call myself like a Bayesian or a frequentist. Like I think they're both just like a great set of tools, and there's downsides to both of them. So for MCMC, it's like, okay, you have to do all the sampling. If your model is simple, fine, that's not too hard, it's not too time intensive. Sometimes that sampling can take a really long time, and then you have to make decisions about burn-in, about thinning, about a whole bunch of other things. So it's kind of like pick your poison, which one, what set of challenges do you want to deal with? Yeah. Yeah.
Is there a set of assumptions we're making? Like we all know the assumptions in the frequentist setting when it comes to like learning model. Is there like a corresponding set of assumptions that we need to
Yeah. Yeah, I mean, I guess you have the power to choose the prior. I guess I don't know if I'd call them like assumptions, but more like you're explicitly setting the model up. So like choosing the prior, and if you choose a terrible prior, that will like be really bad for your results. But that's kind of similar to like if you're doing a t-test and you need to have equal variances and they're just like totally not equal, then that's gonna make things not so great too. Yeah.
And like in this example, we're still, all of the regular assumptions are still being, still have to have equal variance, like that, right? Even though this is.
Yeah, so for this one, yeah, yes, we're assuming like homoscedasticity, like the same vertical variability, whether we're looking at like days that are not humid or hot and days that are like very humid and hot. Yes.
But you could change that.
But you could change that, yeah. But just like in frequentist statistics, you could change that too. Yeah. I guess all of it is like, okay, how hard do you want to work? All right, Kim.
Sorry, asking so many questions, but you know, sometimes I hear people saying that they do Bayesian because it deals better with collinearity or multicollinearity in the models. Is that true? Like, how do Bayesian models deal with collinearity?
I think it could partially depend on the sampler that you're using and how good it is at dealing with it. So like some samplers do like update one component at a time, like, okay, first we'll update the slope, then the intercept, then the variance, then the slope, then the intercept variance. Or other samplers like update it all at one time. So maybe that could affect it. Do you have any ideas about like?
Yeah, I think there is also another type of prior which called shrinkage prior. So it actually, has sort of like a similar function as like in frequencies we use lasso or reach for deal with this kind of questions.
Yeah.
So you mentioned that normally you wouldn't like thin. When do you thin? Why?
Yes. So like say your posterior inference is very expensive, but storage is very cheap. Like storage is easy and the computation of the posterior stuff is expensive, then that's when you would want to potentially thin. So it's like a kind of trade-off, balance those two things. Yeah, great question. Yeah.
So I heard from somebody that they said if your model converges quickly, it's more likely it's right. Is there any truth to that?
I think if it converges more quickly, there's less of a chance you're, as the user, gonna ruin it. Like in this linear regression one, it's like practically already converged almost because it's like starting to sample at the right place. If you start to sample at like totally the wrong place, it'll take some time to get to the right place to sample. So, but like if you run it long enough, then.
Like if I run it over a weekend and it still hasn't like found convergence and
it's so hard because like some models are so simple and running it over a weekend would be like so overkill that you'd be like totally safe, and other models are so complicated that running it over the weekend is maybe, I mean, depending on your computer, like not long enough. So it's like really tricky to say.
All right, we better call it for lunch. Can everyone meet downstairs again for a quick picture and then head off to lunch? Thank you to our speakers.